Gambler's Ruin. Player A has $1 and player B has $2. Each play gives one of the players $1 from the other. Player A is enough better than player B that he wins 2/3 of the plays. They play until one is bankrupt. What is the chance that player A wins? We will discuss two possible solutions to this problem. These solutions will solve for the general case of this problem and arrive at the same answers. Let's look at the first solution. We will say that the player A has $8 and player B has $B at the beginning. Let's tabulate a few possible values each player can have. Again, player A and B start at A and B values respectively. If player A wins, we get A plus 1 versus B minus 1. If instead B wins initially, then we get A minus 1 versus B plus 1. This continues for a while, and if A reaches A plus B first, then A wins. If B reaches A plus B first, then B wins. Note that the total amount of money is conserved, which is A plus B. Because of this, we can just track only one player's money, and it becomes a one-dimensional random walk problem. Therefore, let's focus on the player A's balance only. Let's draw our x-axis that will hold the one-dimensional random walk. Our chosen player A starts at x is equal to A. At x is equal to 0, player A loses, and at x is equal to A plus B, player A wins. It can take a step to the right with a probability of P is equal to 2/3, and to the left with a probability of Q is equal to 1/3. Here, x is equal to 0 and x is equal to A plus B are absorbing states that terminate the random walk process. So we have two boundary conditions. Actually, if B has infinite amount of money, then the problem reduces to the one with only one boundary condition. This was discussed previously in the cliffhanger problem in this channel. In that problem, the probability of falling over the cliff, or A losing, was Q divided by P to the power of A. Let's call this Q over P ratio as R for simplicity. We will use the cliffhanger's result, where B had infinite amount of money, to derive the solution to the current gambler's ruin problem. Now, let's give names to some important events. Let L show the event that A loses. Let X, A plus B, show the event that A reaches X is equal to A plus B at some point. Now, let's use the law of total probability for A losing and condition it on A reaching A plus B event. Probability of A losing is equal to R to the power of A, which is equal to probability of A losing given that it reached A plus B, multiplied by the probability of A reaching A plus B, plus the probability of A losing given that it never reaches A plus B, multiplied by the probability of A never reaching A plus B. So what are these terms equal to? This last term is the probability of A never reaching A plus B, which is the probability that it loses in the gambler's ruin problem. Let's call that Q. This term is the probability of A losing if it cannot reach A plus B. It has to be 1 because if it never reaches A plus B, then it cannot win by definition. Next, this term is the probability of A reaching A plus B. It is the complement of the other term, so it has to be 1 minus Q. Lastly, this is the probability that A loses if it reached A plus B. Again, remember that this equation is still in the framework where B has infinite amount of money. So this has to be equal to R to the power of A plus B. Let's rewrite this equation for clarity and find Q from here. Now we have the Q, which is the probability of A losing, as it represents the event of A never reaching A plus B. But the problem asks us to find its chance of winning. So we write PA is equal to 1 minus Q, and after simplification, we get this expression. Again, R here is Q over P. Note that if Q is equal to P, which means R is equal to 1, we get 0 divided by 0, so our answer becomes undefined. But in this problem, we have Q is equal to 1 over 3 and P is equal to 2 over 3, giving R is equal to 1 over 2. Substituting this R gives 4 over 7 as our answer. For the problematic R is equal to 1 case, we need to use the L'Hopital rule by differentiating the numerator and the denominator with respect to R. Carrying out the derivatives, we get A divided by A plus B as our answer for R is equal to Q over P equal to 1 case. This is the case where the left and right steps are equally probable, and it can actually be derived much easily using a martingale approach, which we will not discuss here. Now let's move on to the second solution. Here is our x-axis again for the player A. This time we will use a recurrence relation. Let Pi be the probability of reaching n is equal to a plus b from an arbitrary position I. Then the expected value of Pi can be written using the next step values. Pi is equal to P times Pi plus 1 plus Q times Pi minus 1. Let's find Pi plus 1 from here for future use. Now I want to find how the probabilities differ between Pi plus 1 and Pi. Substituting the Pi plus 1 from the above gives the following relation. Again, let's call Q over P to be R and rewrite this equation. Note that we have boundary conditions of P0 equal to 0 and Pn equal to 1. Namely, A has a 0 chance of winning if it hits x is equal to 0 and 100% chance of winning if it hits x is equal to a plus b. Now, let's start plugging in different values of I to see if there is a general expression for Pi. For I is equal to 1, we get P2 minus P1 equal to R times P1 minus P0. Since P0 is equal to 0, we have P2 equal to P1 multiplied by 1 plus R. Now for I is equal to 2, we again use the above recurrence relation. Then substitute P2 from the I is equal to 1 case. At the end, we get P3 is equal to P1 multiplied by 1 plus R squared. Overall, for general I, we see that Pi has the form of Pi is equal to P1 multiplied by 1 plus R squared plus etc. up to R to the power of I minus 1. But how do we find the P1? We need to use the other boundary condition for I is equal to n. Then Pn is equal to 1, which is equal to P1 multiplied by 1 plus R squared, etc., up to R to the power of n minus 1. In general, if R is not equal to 1, then this is a geometric series with a known solution. Let's call this term y, then it can be found as follows. Plugging in y to Pn, we get the following expression for P1. Note that for r is equal to 1, P1 gives 0 divided by 0, which is undefined. The same thing can be said for y. For r is equal to 1 case, y is simply the sum of n ones, so y is equal to n. This gives P1 is equal to 1 over n for r is equal to 1. Now let's come back to the general I case. Here, using our geometric sum result, we can rewrite Pi. Note that we can cancel the 1 minus r if r is not equal to 1. For r is equal to 1, we get Pi is equal to P1 multiplied by I, which is equal to I over n. In our problem, we had I is equal to A and n is equal to A plus B. Substituting those gives the same answer as in the first solution.